welcome Javier Rubio from University College London, who will now tell us about his work.
Okay, thank you very much. So thanks everyone for coming, and also I would like to thank Pantelis for the kind invitation. It's also nice to be back at Cambridge. Last time I was here was in 2012. So I was still young and full of illusions. So, so thanks everyone for coming. So I will today I will talk about a recent work which is called dynamic survival analysis, and is based on modeling the hazard function using ODEs. This is a joint work with Professor Andres Kristen from CIMAT, Mexico. And for those of you who don't know him, he was one of the members of the scientific team who led the pandemic, the COVID-19 response in Mexico. So he's actually, he used to work a little bit on ODEs, where this idea basically originated. So the overview of the talk is as follows. First, I'm going to present a motivation and a little bit of related papers about this topic. And then I will focus mostly on presenting some examples. The first one is one that related to a topic that I like, which is about how to generate new probability distributions with this approach. But that's not the main aim. After that, I'm going to illustrate a distribution that is not included in the usual catalog of distribution that we use for survival analysis, that can be generated using the proposed approach. And after that, I'm going to present a slightly more challenging model, which is what we call the hazard response model, and it's a model that doesn't have an analytical solution to the ODE. And I am going to mix example 2 in the real data application to explain all the other components like the likelihood function, the priors. This approach can be used using likelihood-based estimation or Bayesian estimation. In this case, we will focus mostly on the Bayesian approach. And then I will also explain some of the computational challenges behind this approach. And then I will conclude with a general discussion and some of the available software. Okay, so as you know, survival analysis has been applied in many areas. It's one of the main branches of statistics. In my view, it has, in real data applications, it has always been popular. But in the academia, in methodology and theory, it has had ups and downs. A lot of research was done with flexible parametric and semi-parametric models. Then it kind of went quiet for a while until the machine learning people discovered survival analysis and started doing a lot of research combining machine learning methods and survival analysis. Then I felt like it went a bit quiet again, and now it's coming back. It's having another comeback with causal inference and survival analysis, conformal prediction, survival analysis, and so on. But I feel that it has in applications, it has always been there. So the main quantities of interest in this framework is, of course, the survival function and the hazard function. And there are, of course, many other quantities that can be obtained from the survival and the hazard function. Apologies if this is just basic notation, but I thought it was still important to introduce a little bit of notation. So the survival function is simply the probability of surviving beyond time t. While the hazard function, as you know, is given by this limit, is an instantaneous failure rate. And as per some algebra, you can write it down as the ratio of the probability density function and the survival function. And it has some appeal for quantitative analysis. Most of the regression models in survival analysis are based on the hazard function, perhaps due to historical reasons. But there is also an appeal in terms of qualitative analysis, like trying to understand the evolution of the hazard function a long time. That's something that I'm going to present in one of the real data examples. And then, of course, this is only, the hazard function is only of interest in deeper analysis, where you actually want to see the evolution of the disease rather than some routine analysis where you may only be interested in calculating survival probabilities at specific time points. Okay, so now we have the, I'm just gonna check if I can move this here. This one.
Yeah.
Perfect, thank you very much.
The people.
I don't know if you can.
Oh,
No, just wait.
Okay.
yeah.
Okay.
That will be fine if you close.
Okay. No, this one, how can I? So now how do we estimate the hazard function? If that's our interest, then of course there are parametric methods, fully parametric methods based on using a distribution plus your favorite estimation method. There are semi-parametric methods based on using some splines on the log hazard or the cumulative hazard function or etc. in your favorite estimation method. And then there are, of course, fully non-parametric methods based on KDEs or even Bayesian non-parametrics or so on. I haven't really come across machine learning methods fully focused on the hazard function. There are many methods to study the survival, but fully focused on the hazard function, I haven't come across that many. So if you know any, I will be interested in hearing about them. There is one that I'm going to present in a moment. Now, advantages and disadvantages. So take this with a pinch of salt, of course. I'm not going to defend any of these points to death, but if you're using a parametric approach, one of the challenges is the limited flexibility. Like if you use a Y-1 distribution, it can be increasing or decreasing, and that's the end. If it is a log normal, it's only unimodal, and so on. But then, of course, you can use distributions that are more flexible. Now, with semi-parametric, they are very flexible, of course. They can be slightly harder to implement. And if you are not careful in penalizing carefully or choosing the nodes carefully, you may end up with something a bit wiggly. And then interpreting wiggly hazard functions is a bit challenging because then you don't know whether it is a phenomenon which is due to the data, to the characteristics of the data, or just because you are overfitting. Non-parametric models have the same disadvantages, I would say, but they are of course very flexible. Okay, so what are the aims of this work? So what we are proposing is to parametrically modeling the dynamics of the hazard function. And we are going to do that using a system of first-order ordinary differential equations whose solution is positive because the hazard function is a positive function. So we are only focusing on ODEs with a positive solution. And of course, this framework is of interest to people interested in understanding and interpreting the evolution of the hazard function, not necessarily only on estimating or calculating survival probabilities. I will focus on the case without covariates, which is where we are now, but I will also conclude with a discussion about the strategies about how to include covariates into this framework. So a little bit of notation. Suppose that O1 to ON is what I call the original survival times that we may not necessarily observe. CI represents the right censoring times. And then what we actually observe are TI, which is the minimum between the survival time and the censoring time. Delta I is the vital status indicator. 1 if it is uncensored, 0 if it is censored. And just for completeness, I am including what I am using here. It's really basic, I understand. The survival function is S, the CDF is capital F, the PDF is little f, the hazard function is little f, and the cumulative hazard function is capital F. Okay, so this is just the basic notation in survival analysis. Okay, so what we are proposing is, suppose that we have a collection of differentiable functions, Q1 to Qn, and then put them together with the hazard function in a vector, which I'm going to call y. And then we will define a system of ordinary differential equations using that y. So the derivative of y, which is the derivative of all of the terms here, is equal to a function here. This function, in the context of ordinary differential equations, they call it the right-hand side. So very original. But it's just, also they call it a vector field. It's just a function of all of these quantities here, or all of these functions, and potentially t as well. And also, we are adding one more state, which is that the derivative of the cumulative hazard function is the hazard function. From a mathematical perspective, this is trivial. We know that's obvious. But from a practical perspective, this is very important because it means that the solution of this system will give you the hazard function and the cumulative hazard function. And then we know that the likelihood function can be written when you have the hazard and the cumulative hazard. So that's the reason why we are adding this additional term. And then we have some initial conditions that I'm going to discuss more in detail, which are the initial conditions for all of these quantities here. Any questions so far?
Psi theta is are the parameters, aren't they?
Yeah, theta are the parameters. Good point. So this is a parametric function. I am assuming that it's a parametric function, and this is just a generic function. But of course, we are focusing on functions that will lead to a positive solution for H, but it's parametric. Any other comments? What?
You speak about Q later. How do you?
Yes, of course. Q are hidden states, and I will discuss what additional. So what is this additional term adding to modeling H? I will present particular examples, but the idea is simply to enrich the model at this point. Okay, so this family, this is a system of ordinary differential equations. They contain the hazard function as a solution. And so if you fix the initial values and the parameter theta, they will retrieve a solution for the hazard function and the cumulative hazard. So the cumulative hazard function is also included because we are going to need it. That's the reason why. Mathematically, including that additional state is trivial. And so the initial conditions will include, for instance, that the hazard function at time 0 takes some value H0, which is positive, non-negative, and finite at time 0. And then in the real data example, I will discuss how to fix this initial condition, or also it is possible to estimate these initial conditions. So the solution may be in closed form, as in example 1, or you may need, it may not be available in closed form, and then you will need a numerical solver. So what we are arguing here is first, that there are many differential equations that we can take advantage of. People have been using ODEs for more than 300 years. So there is a huge catalog of ODEs already. People have also been working on solvers. They are really fast now in R, in Python, and I have been recently exploring Julia as well, and they are really fast. So computation is not a big problem here. So a related work, I am only going to present, we have a proper literature review in the manuscript, but I'm only going to discuss one, which is the most recent. In a paper, sorry, in 2023, they proposed modeling the dynamics of the cumulative hazard function using this equation here. So instead of having the hazard function, the derivative of the hazard function, they have the derivative of the cumulative hazard function, and then here they have the random field. So the first difference is that they only use a one-dimensional ODE. They do not consider systems. Second one is they are modeling the dynamics of the cumulative hazard function, which we know is the hazard function. So they are modeling the hazard function. And so I'm not saying this as a criticism, because that's exactly what they wanted in their papers. But what they are doing is modeling the hazard function, which is something that we have been doing since the times of Cox, basically. And so what they do is in their 2023 paper, they use this formulation to produce a new type of estimators, not semi-parametric estimators, but they still coupled with well-known hazard structure, proportional hazards, accelerated failure time models, and etc. Because they are modeling the hazard function actually, only through a different lens. And in 2022, the same authors modeled the random field psi using neural networks. So basically, what they are using is using this formulation to create a new device to estimate the hazard function, either using semi-parametric methods or neural networks. And also, in our case, we have a system of ODEs. So we allow for including more states in the model. Okay, so that's basically the brief literature review. I am going to start now with another, this is partially a literature review. And if you look at the hazard function, which is, as you know, the density divided by the survival, and you calculate the derivative, you end up with a differential equation. So the hazard function satisfies this differential equation, and this function here, A, is the logarithmic derivative of the probability density function. And this was almost simultaneously proposed by two papers in 1896 and 1987, where they found that this ODE is a Bernoulli type differential equation or a Riccati type differential equation. This is just the way that you write down the differential equation. Something that they didn't notice is that if the term A depends on T, what you have is what is called a non-autonomous ODE, because now it depends on H and depends explicitly on T. If A only depends on H, what you have is an autonomous ODE, because it only depends on H, the right-hand side. And this has important implications because one-dimensional autonomous ODEs only have monotonic solutions. So for instance, we know that the y-wall can only be increasing or decreasing, then the corresponding ODE is going to be autonomous. The log normal is unimodal, then it is not monotonic, then the corresponding ODE is going to be non-autonomous. And then, so this function A represents a sort of autonomy coefficient that basically separate distributions into two. The ones that lead to autonomous ODEs and the ones that lead to non-autonomous ODEs. So it's very tempting to think about this equation as characterizations of distributions. And that's exactly what they did. These papers claim that they have produced a new characterizations of distributions based on ODEs. However, as you can see, in our formulation, we can produce new hazard functions, and we have additional states. And if you have additional states, you cannot reduce to a one-dimensional ODE. That will be amazing, because then we will be able to model large systems of ODEs using only one-dimensional ODE. And then, and in particular, to Bernoulli type ODEs. So this is not necessarily a characterization of ODEs. So they are missing some distribution there. So what kind of distributions? Another thing that we notice is that most of the distributions, if you look at the limit of t when t goes to 0 of the hazard function, they only start at 0 or at infinity for most of the distributions. So in our case, we allow the hazard function to start anywhere else. So the simplest example using our formulation is we need a model that has a positive solution. So the natural candidate is a growth model, either a population growth model or any type of growth model. You just plug it in there and you are going to get a positive solution. And then the simplest growth model is the logistic growth model. So that's exactly what we are doing here. We have the logistic ODE here, and additional thing that we are adding to retrieve the cumulative hazard. And then we have also some initial conditions. So the nice thing about this model is lambda represents the intrinsic growth rate, is how fast the hazard grows or goes down. Kappa is the carrying capacity, the upper limit or the lower limit. And H0 are the initial conditions. And so the next thing is it has an analytical solution. So we have an analytical solution for the hazard function. And in a sense, this is a new model. And another nice thing is that the cumulative hazard function is also available in closed form. And the initial conditions can be estimated as a parameter as well. And in the first example in the manuscript, we have an example where we can actually estimate the initial conditions. But of course, you can think about setting the initial conditions otherwise, which is what I'm going to do in the second example. Okay, so the second example is what we call the hazard response model. This is an adaptation of the popular Lotka-Volterra equations. And basically what we have here is, if there is no competition, the hazard function is growing using a logistic growth. And also, what we are adding an additional state, which we call the response, is also growing using a logistic growth equation. We're assuming that they have the same carrying capacity, because the response is not going to go beyond what is competing to, in this case. That's what we are assuming. They have different growth rates, and when alpha is different from 0, they enter into competition. And we don't think that, so the way we divide this is, we are not thinking that the response is attacking the hazard function. They are in competition. So the hazard can win. So we are allowing the hazard to win. And also we are assuming the same alpha, because that will restrict the model as I will discuss in a moment. So these two things are competing. It's basically like two species in competition. And one of them will win. And this one doesn't have an analytical solution. So we will need a solver. Okay, so that's exactly what I just said. And then we have also presented some additional technical details in the manuscript. But one technical detail that I wanted to discuss is the following. So something of interest in the analysis of ODEs are the analysis of attractors, which is basically which are going to define the shape of the hazard function, basically. So what state is this ODE converging when the time goes to infinity? And to analyze that, we need to define these two quantities, H star and Q star, which are nothing but simple functions of the parameters. So the equation has parameters lambda, beta, alpha, and kappa, and the initial conditions. And alpha star and Q star are functions of those parameters. So if Q star, you calculate Q star, and this is smaller than 0, then the response loses the competition, and it will allow the hazard function to grow to its carrying capacity. If H star is smaller than 0, then the response wins the competition, and it is going to bring down the hazard function to 0. And if both are positive, then they will reach an equilibrium. So these are the three types of attractors that this type of model will allow. This type of restricted competitive local terra model will allow. And we don't have oscillations in this model due to the restrictions that we made. But if you allow for different carrying capacities and different alphas, so the alpha and alpha prime, alpha tilde here, for instance, that will produce a model that leads to oscillations. But that's exactly what we don't want, because, as I said, interpreting oscillating hazards, especially hazards with a seasonal effect, is slightly challenging. Or I have never come across an example where you have something like a hazard function that goes up and down. But if you have one, then of course you can generalize this model and try to address that. Okay, so now to fix ideas, let me present the real data application. In this application, we analyze the popular Rotterdam data set from the survival R package. This data set contains 2,982 information about this number of patients, breast cancer patients. It's an observational study. And out of this, 1,272 died within the maximum follow-up period, which is around 19 years. So we know that some of the patients receive hormonal treatment, chemotherapy, and also surgical treatment. We don't know exactly at what point. We only know that they have received treatment, some of them. So we expect that the evolution of the population over time will depend on this type of treatments, and of course the natural response from the immune system. And so we thought that the hazard response model may be a good model to account for the fact that there is a hazard function and there is a sort of intervention that is pulling down the hazard function. So they will be in competition. The minimum survival time in the data is 45 days. So at the beginning, we said we are not going to have information about the initial conditions, especially because we need two initial conditions, one for the hazard function, one for the response function. And we verified this by fitting the model. We found that the model can estimate H0, but not Q0, in the sense that you put a prior, the likelihood will be kind of flat, and your posterior will look like the prior, basically. So what we said, okay, let's take this opportunity for illustration to say how could we fix both H0 and Q0 using information from this type of data. Then we have a likelihood function, which depends on the parameters theta of the model and the initial conditions that we are going to fix in a moment. And as you know, this depends on the hazard function at the observed times and the cumulative hazard function evaluated at all times. And that's why we are adding this additional step, because then we will obtain both functions as a solution to the ODE. And given that you have a numerical solver, you just tell the solver, give me H and capital H at these times. That's basically what you do. We have used some weak informative priors. I don't think there is anything massively interesting about just priors that we did. We just try to be not too informative. But of course, it would be nice if we could put some information into the prior. To fix the initial conditions, we have used, as you know, prognosis of breast cancer patients is relatively good, at least compared to other cancer sites. For the first few months, so we will expect that mortality will be low in the first couple of months. And then what we have assumed here, and it is open to debate, is that the survival time at the first month is going to be around 0.999. So the choice is relatively robust as long as you don't go too far. I mean, of course, if you say 0.1 instead of 0.99, you will obtain completely different results. But as long as you have a high survival at the initial time, it is not going to be too different. Then the hazard function at time 0 is the derivative of the survival at 0 divided by the survival at 0, and using simply the definition of the derivative. This is, and replacing the corresponding values, we get an initial condition around 0.01. Now, another point that fixing the initial condition, then again, this is open to debate. For the response model, well, here I said treatment, but this is the response. We think that this is an observational study, so we don't expect that everybody will be assigned to a treatment from time 0. And treatment may take some time to kick in. So we set this value to a very small value. In this case, we are using 10 to the minus 6, but this you can of course play with the initial value, and as long as it is not too different, you will get very similar results. Okay, so now we have the model. So how do we do the computations? So I did the implementation in R, and my colleague did the implementation in Python. And I have used this solver, LSODE, from the R package DSolve. And it is quite good, it's very fast and robust. The solver requires the Jacobian of your model. So it allows you to either calculate that Jacobian numerically, but then that will add more errors, or to calculate it explicitly, and that's what we did. We calculated the Jacobian explicitly to avoid additional errors, numerical errors. This is just computational thing, but we have also implemented the model in terms of the logarithm of that, which makes the performance of the solver more stable. And to obtain posterior samples, my colleague used the sampler called the T-Walk, because he invented the T-Walk and he implemented the T-Walk. And on my side, I used an adaptive metropolis Hastings. So I went for a slightly safer choice. And then we have used the usual in several initial points and etc. And he didn't do it, he's more Bayesian fundamentalist, but I also included an analysis of maximum likelihood estimation for all of the real data applications. So you can do maximum likelihood estimation or Bayesian as you prefer. And we obtain a posterior sample of say 10,000 with a thinning of 100 and a burning period of 10,000, simply to show that we can actually run the sample for long periods. And this is what we obtained. This is the predictive, the red line represents the predictive hazard function. As you can see, it was going up, and then at some points it was pulled down, and it looks like it has stabilized. The yellow line represents the response, which seems to kick in at around 2 years, and that's exactly when the hazard function starts going down. And then from there it goes up, and then they seem to be stabilizing. And then, of course, we can obtain the usual posterior predictive survival analysis and calculate the survival probabilities at specific time points. Another interesting thing is that the values of H star and Q star, which define the state, whether the hazard function wins or the cumulative or the response wins, or they are in or they stabilize, is simply based on the posterior distribution of these two. So we can actually calculate the posterior distribution of the state. And in this case, we found that with probability very close to 1, the state is stability, meaning that they will stabilize at a point H star. Okay, so what we have found for this specific data set is that the hazard function had this increasing behavior. The response, which is a combination of many things, kicked in at around 2 years, pulls down the hazard function, and then that is the reason why the hazard function goes down. And in this case, there was an equilibrium, so we didn't find that either the hazard function or the response function win. And also, this is also what we were. So we found that this is actually what Royston and Palmer did found in 2002, where they actually calculated the hazard function using splines, and they tune the choice of the nodes and etc. And they actually found that around 2 years there was a change in the behavior of the hazard function. But perhaps there are people on the audience who can explain it better. Okay, so that's basically what I have to say about the proposal. Yes, now just some final discussion. So we have proposed an approach. We believe it is relatively novel, of course, acknowledging some of the related works. For modeling the hazard function via systems of ordinary differential equations. Then we acknowledge that this may only be of interest to researchers who are actually interested in a qualitative analysis of the hazard function, not necessarily only on the quantitative part. And of course, flexibility is not the main aim, although we can obtain very flexible models as well here. So we have produced R code and Python code for the results. And this is just a side comment, but I came across this project in Julian. It's called SciML. And they have some ODE solvers, and they claim that their solvers are 100 times faster than those in R. So I'm really looking forward to that. I hope it is true. Okay, so now what can we gain by adding additional states? Another popular model in the modeling of the population growth or competitive species is the use of ODEs with a lag or this type of term. And this is basically a term that is not only considering the hazard function at time t, but also the entire evolution of the hazard function, weighted by some function g, which in this case is given by this quantity here. So now this becomes an integral differential equation, and the additional thing we are gaining is including a sort of time-dependent effect of the hazard function. So depending on the history of the hazard function, that's how the response is going to fight the hazard function. And now this is an integral differential equation, but this is nothing but a convolution, and then we can rewrite it by adding one more state. So the aim of this example is to show that adding states is not just about adding flexibility to the hazard function, but also to adding some terms that have a more specific interpretation. Now, what about covariates? Of course, I have focused on the context without covariates. The natural way would be, okay, use the solution of your hazard function or your ODEs as a baseline hazard for proportional in your proportional hazard model, accelerated failure time, and some others. But then what we thought, my colleague and I think, is that this will be like a glorified way of producing baseline hazards. So to fully take advantage of this approach, what we think will be more interesting is to model the parameters using a transformed linear or analytic predictor, because then if we are claiming that ODEs are very interpretable, they have interpretable parameters, then if we model each of the parameters, we will try to understand the effect of the covariates in the model. But nothing prevents you from using the first one, of course. And then, of course, this can be naturally extended to other frameworks, such as using pure models, spatial models, or relative survival, which is very popular in cancer epidemiology, and etc. So these are the references that I have been mentioning throughout. So I thank you very much for your attention. Do you have any questions?
How do you handle risk with that?
We have
The Q will compete against the risk.
Yeah, that's a very interesting question. We don't see this as a competing risk model like in the classical sense in survival analysis. We are just adding a term here that is in competition in the sense that they are acting in the same scale, but it's not necessarily a competing risk in the classical sense, because we could take this model here and put it into a competing risk survival model as well.
No, but I mean, if you had a competing risk, risk, what does that handle? How does the Q, yes, the Q, when it's a hidden seed?
Yeah,
That's
an even more interesting question indeed, because I mean, we can translate what we have here into the classical competing risk framework. Now, how to include the competing risk as a state, I don't have a direct answer. And I think that will be interesting to see if we can include a competing risk through a state. I don't see it right now, but that's an interesting question. But of course, what you can do is to bring this into the competing risk modeling, but that will be just repeating the same that everybody is doing. But certainly, how to include a competing risk here, I don't see how, but I don't think it is impossible. Yeah, very interesting.
It's very nice. Thank you very much. I was wondering what would happen to this example that you showed us in the breast cancer if you said alpha, the alpha parameter equal to the means
They will become independent, and then you cannot really estimate the parameters of this term here.
No, but you can estimate the hazard.
You can estimate the hazard, yeah. You can remove, if you say there is no competition, then there is no reason to necessarily model Q. But then you can have, you only have the logistic growth model, and then you go back to the first example that I presented. Because if alpha is equal to 0, then you remove all of this, and then you have a closed form solution.
But would the hazard of this example look very different?
Yes, because if you remove this term here and this state, you're actually allowing only for, because this is now an autonomous ODE, because it depends only on H, then the solution will only be increasing or decreasing. And so in that sense, you will not be able to capture this shape, the kind of unimodal shape. So in that sense, adding this additional term is adding flexibility to the hazard function as well.
Owen, online, please. I think you can unmute yourself, right?
Yes.
Yeah,
Thank you.
Mute us and then.
Am I audible? Can you hear me?
Yes.
Okay.
Yes. Oh dear.
Thank you. Javier, thank you very much for a great talk. This will be a very trivial question, because I know you have designed your ODEs to ensure positivity of the solutions, but I was struck by the fit to the Rotterdam data as looking like very much a slightly underdamped second order linear system. And I wondered, when it comes to interpretation, how important it is to, how shall I put it? How important it is to have, I didn't think that an underdamped second order system would actually be any more restrictive than what you've got in terms of constraints. But your system is much more nonlinear, and yet the solution appeared to pretty much be well modeled by a second order system. I wondered if you had any comments.
Yes, I mean, you can use the more general model, as I said, with different competing parameters and different carrying capacities, allowing now for the solution to be oscillating. That's possible, but of course, there is always a cost. Adding parameters into a model, there is will always incur in a cost. And actually, we tried this kind of models, and you end up with the same type of models, but with very wide posterior distributions. So it is the uncertainty, the effect of adding more parameters and enriching the model will, of course, have an effect in your inference. But if you have enough data and your hazard function is complex enough, then considering the full model will, of course, be a possibility. We have also considered other models like the harmonic oscillator, but translated to the positive side. And it produces, it's also very tractable, but we couldn't find like a really nice application of a hazard function that will be oscillating like a spring. Okay. Yes.
It's me. No, I've got lots of questions. I I have all of them. I mean, diseases that sort of seasonal.
Yeah.
Could have and
This kind of seasonality, yes.
yes.
I think, yeah, we are not saying that these models are not of interest for the applications that we had in mind and the data also that we had available. We didn't need something oscillating, but I think it will be interesting to see if there is something, there is another type of models where the oscillations can apply. Then, of course, one of the questions that I always have is about using survival analysis in infectious diseases where you can get cured. So how do you exclude the patients from the model, and whether using a single hazard function will make sense, or if you need a more complex model that will take into account that maybe different parts of the hazard are determined by different cohorts or different groups. But that's an interesting thing.
The other thing that makes me think is, okay, so you're proposing this ODE version as an alternative to other sort of non-parametric model. Have you understood, for instance, situation in which this is a more flexible model than a spline?
Mm-hmm.
I mean, the splines obviously
Yeah.
It depends on how you choose. Yeah.
Generalized gamma.
Yes, I know, but at least non-parametric or semi-parametric, I was thinking. Yeah.
Against the use of general distribution, which is also a topic that I like, all distributions will always start at 0 or at infinity. So in that sense, they are slightly less interpretable. And also they will never stabilize like the generalized gamma. They will always go to 0 or increase or decrease. power generalized y will exponentially take y will all of those. But then there's something that kind of bothers me is the initial condition that is always fixed to 0 or infinity. And if you are really interested in looking at the evolution then of the hazard function, that's something that you're already saying about the model. It starts here or here at infinity, but never something in between, which is what we will expect, that the hazard function starts somewhere, at a positive value. But certainly, I mean, so what we are trying to avoid is the flexible battle, because of course, if you use something fully parametric or something parametric, then you can obtain flexible models as well.
Yes, you made an analogy between a biological process and a system of ODEs that you're going to use for a problem, right? So for the response have a meaning.
Yeah.
If you believe in that biological process, you might want to use some more informative prior. Like how would you translate your prior information?
Well, in that sense, you can think about two ways. So whether you include it in the model or whether you include it in the prior. I saw a paper that was modeling the growth of the tumor or of cancer tumors, and they say the hazard function has to be proportional to the size of the tumor. So they were assuming that the way that the tumor grows is the way that your hazard grows. So you could try to include that information in the model. So for instance, for a cancer disease, that's a possibility if you have enough information and enough confidence on that model. If you want to include it into the prior, then the idea is to understand the interpretation of the parameters. So for instance, whether you think that there will be a very strong response, then of course you will need to put a prior on very high values a fast response on high values on beta, or a slow response, then you will need to translate that information into the interpretation of the parameters. So the idea of ODEs is that they have interpretable parameters, and that's something that Bayesians like, because then you can translate your information. But of course, the question is whether or not you have reliable information to be translated. Yes, please.
Maybe it's probably a stupid question, but I'm just thinking about, we have a lot of interest in things like unmarking here because we're modeling the continuous covariate and survival.
Yeah.
Is there a way of putting that into this framework?
Again, well, this is a relatively new. I'm also trying to understand this type of framework. With landmarking, that will be interesting because I guess what you are thinking is about moving the time, right, and refitting, or in...
I'm thinking about the underlying problem, which is simultaneously modeling a continuous biomarker and survival scenarios depending on the biomarker, so a joint model, and landmarking is one way of getting around the computational differences that includes.
Yeah.
I wonder if this. I haven't got past the I wonder if there's a way.
Well, I am at the same state, but I would say that perhaps we will need to say, if we want to model the effect of a specific covariates, we will need to think that, for instance, if we have something that is affecting the response, then we will try to model it through the corresponding state.
Yeah.
That will be a possibility. For instance, something that we have already tried is using this what is called the logistic ODE for clinical trials. And then we consider that they have the placebo and the treatment, or treatment 1 and treatment 2, have different lambdas and kappas. And then this allows for crossing hazards and etc., and crossing survival functions or parallel as well. We haven't got to the point where we have an additional state, but that's a really, really interesting question, because it's how do you include that information into the different states? And we are still working on that. And so far, we have also some computational challenges there. But that's a really, really interesting question.
Are there any questions online? If not, then thank Javier again. Thank you.